If we want to understand the microprocessor revolution of the 1970s, we have to start with its physical reality. These white ceramic dual inline packages with their rigid rows of gold pins were the tactile foundation of early computing hardware. Specifically, this is the Intel 8085. It is an 8-bit microprocessor manufactured using NMOS technology, designed to execute instructions and manipulate data 1 byte at a time. To function as the central processing unit of a computer, it faces a strict computational requirement. It must access a 64 kilobyte memory map. Doing that requires a 16-bit address space, meaning the processor has to generate and output 16 distinct binary signals just to locate a single piece of data. It runs on a single plus 5-volt power supply, and instead of relying entirely on external hardware for clock generation, the 8085 includes an internal oscillator. Connect a 6 MHz crystal, and the chip divides it by 2 to operate at a steady 3 MHz frequency. To truly understand how this architecture operates, we have to map its internal logic abstractions onto a strict physical limitation, a boundary of exactly 40 pins. This diagram shows the strict hardware constraint of the 40-pin dual inline package. Every single pin must be meticulously assigned to route power, timing, and data. We start by grouping the baseline operations. Pin 40 provides the 5-volt power supply, pin 20 is the ground, and pins 1 and 2 receive the external crystal input to synchronize the internal clock. Next, we map the dedicated upper address bus. Pins 21 through 28 are entirely unidirectional, responsible for carrying only the most significant bits of the 16-bit memory address out to the system. Here we hit a physical bottleneck. Pins 12 through 19 are multiplexed. These 8 connections are responsible for transmitting the lower 8 bits of the memory address, and then they are reused to carry the actual data payload. Finally, we have the control and status signals. Pins 29 through 34 act as the processor's command interface, issuing the reads, writes, and alerts required to drive external hardware. These 40 physical connections are the absolute only mechanism the CPU possesses to orchestrate an entire external motherboard. This diagram illustrates the macro 3-bus architecture, connecting the internal CPU to external components. The red pathway represents the 16-bit address bus, which is strictly unidirectional. Addresses only flow out to target a specific location. Below it, the 8-bit data bus is bidirectional, allowing binary information to be fetched into the processor or stored back out. This creates an immediate mathematical problem. A 16-bit address bus and an 8-bit data bus require 24 separate physical pins. Subtract the power, clock, and control pins, and the physical chip lacks the space. The solution is time multiplexing. The upper 8 address bits use dedicated wires. The lower 8 address bits and the 8 data bits alternate sequentially over the exact same wires. To prevent confusion, a synchronous pulse called address latch enable, or ALE, fires when the bus holds the address, alerting external logic to capture those bits before data arrives. Multiplexing successfully solves the physical pin constraint, but it transfers the burden of that complexity directly onto the control and timing systems. Because the 8085 uses the exact same address lines to target both memory chips and I/O devices, it must actively broadcast its current operational intent to the system. It dictates directionality using active low control lines. RD fires to execute a read operation, and WR fires to execute a write operation. To route the traffic, it uses the IO/M signal. This acts as a toggle switch. When pulled low, traffic is directed to the massive 64 kilobyte memory space. When pulled high, traffic routes to the 256-port I/O space. A machine cycle is defined by the matrix of IO/M, S1, and S0. For an opcode fetch, IO/M drops to 0, S1 and S0 become 1, and the RD signal fires. Conversely, for an IO write, IO/M flips to 1, S1 to 0, and WR fires, redirecting data to a peripheral. The timing and control unit acts as a master conductor, utilizing a tiny combination of pins to dynamically reconfigure the motherboard's routing millisecond by millisecond. This internal architecture block diagram lets us transition from the external pins to the internal logic blocks processing the data. The core is the Arithmetic Logic Unit, or ALU, the mathematical center for logic comparisons and arithmetic. The accumulator is the primary 8-bit staging area, holding the initial operand and storing the final result from the ALU. To the right are 6 8-bit general-purpose registers, B, C, D, E, H, and L, serving as temporary data storage during calculations. Because memory addresses are 16 bits, the processor employs an architectural trick, pairing 8-bit registers as BC, DE, and HL to store full 16-bit addresses. Below them are 2 dedicated 16-bit pointers, the program counter for the next instruction and the stack pointer for managing memory subroutines. This carefully arranged register array provides the high-speed workspace required to calculate data and navigate the 64 kilobyte memory map efficiently. This internal architecture handles sequential processing perfectly, but we face a problem with asynchronous external events. How does a processor focused on a calculation loop instantly respond to a keyboard press or a sensor trigger? The answer is the hardware interrupt. These physical signals force the CPU to suspend its current program and execute a specific interrupt service routine. This schematic shows the dedicated interrupt control block situated at the top of the internal architecture. The 8085 has 5 distinct hardware interrupt pins operating on a rigid priority order, starting with a non-maskable trap interrupt down to the general-purpose INTR. They operate on a strict handshake protocol. The peripheral sends an INTR request, the CPU completes its current cycle, and then responds with an INTA, or interrupt acknowledge, pulse. Adjacent to this block are the SID and SOD pins, handling serial input data and serial output data. These provide native 1-bit serial communication directly to the CPU without needing external UART hardware. The interrupt controller transforms the microprocessor from a closed calculation loop into a highly responsive real-time system manager. We synthesize these components by tracing a single instruction fetch cycle. Step 1. The program counter loads the 16-bit address onto the dedicated upper and shared multiplexed lines. Step 2. The timing control unit drops the IO/M line low to select memory and fires the ALE pulse to lock the lower address securely into an external latch. Step 3. With the address secured, the shared lines clear, the RD control signal is asserted, and the memory pushes the 8-bit opcode back over the shared data bus into the CPU's instruction register. This highly choreographed, synchronized dance of buses, latches, control lines, and registers executes millions of times every single second. The engineering elegance of the 8085 architecture lies precisely in its physical constraints. Through time multiplexing and dynamic status broadcasting, a massive 16-bit address space operates securely on a severely limited 40-pin silicon chip. The internal state machine, driven by the unified timing and control unit, orchestrates this external complexity completely invisibly to the end user. The Intel 8085 established the baseline mechanisms, multiplexed buses, hardware interrupts, and precise machine cycles that remain the functional bedrock of modern digital processor design. We can synthesize all these architectural components by tracing a single instruction fetch cycle from beginning to end, observing the system in motion. Step 1. The program counter loads the 16-bit address of the next desired instruction onto the dedicated upper address lines and the shared multiplexed lower lines. Step 2. The timing control unit drops the IO/M line low to select memory and fires the ALE pulse to lock the lower address securely into an external latch. Step 3. With the address secured, the shared lines clear. The RD control signal is asserted, and the memory pushes the 8-bit opcode back over the shared data bus and into the CPU's instruction register. This highly choreographed, tightly synchronized dance of buses, latches, control lines, and registers executes millions of times every single second. The engineering elegance of the 8085 architecture lies precisely in its physical constraints. Through time multiplexing and dynamic status broadcasting, a massive 16-bit address space operates securely on a severely limited 40-pin silicon chip. The internal state machine, driven by the unified timing and control unit, orchestrates this external complexity completely invisible to the end user. The Intel 8085 established the baseline mechanisms, multiplexed buses, hardware interrupts, and precise machine cycles that remain the functional bedrock of modern digital processor design.
Thank you for viewing so far. If it gives you some information, hit the like button and subscribe for more such technical learning.